In this video, we're going to look at studying the rate of a chemical reaction, a branch of chemistry called kinetics. To monitor the disappearance of a reagent, we could use any method of analysis that yields the concentration of that chemical at a particular time. In this video, we'll be using titration to follow the reaction. The particular reaction we're going to look at involves the reaction of propanone with iodine. The products of this reaction are 1-iodopropanone, iodide ions and hydrogen ions. However, reaction schemes like this only tell you the reagents and final products, not the conditions necessary, nor how the products are formed. In this case, the reaction is catalyzed by hydrogen ions. This means that the reaction proceeds slowly in neutral solutions, but much more quickly in acidic solutions. Already, we're gaining useful information that can help us understand how this reaction proceeds. For today's experiment, I want to monitor the concentration of one of the reagents, iodine. To make sure that changes in concentration of the other reagents don't affect the results, the concentration of propanone used will be much higher than it need be. In this way, as the reaction proceeds, the concentration of propanone hardly changes, as only a small proportion is used in the reaction. This is a really important technique in reaction kinetics and is called isolation. We make sure that the concentration of all the reagents are much higher than the one reagent we are interested in, and hence the results only reflect changes in that one reagent. In our case, iodine. We have isolated the results from iodine from all other influences. Here's the setup I put together in one of the teaching labs here at the University of Plymouth. At the moment, the propanone and acid are in solution in this flask, and the iodine solution in this one. They are both in a water bath, and I'll be keeping the reaction flask in there to ensure that there are no changes in temperature. This is in a fume cupboard, as the iodine vapours can be irritating. Once the reaction starts, I'll be taking a 20 ml sample every 5 minutes and placing that sample into one of these conical flasks. These flasks contain a solution that removes the hydrogen ions, which slows the reaction to almost nothing, so that it doesn't continue whilst I'm performing the titration. The titration is performed by reacting a solution of sodium thiosulfate of known concentration with the iodine in the sample. I'll be adding starch near the end of the titration to show a sharp endpoint. So let's start the reaction by adding a known volume of the iodine solution into the flask containing the propanone and starting a clock. As we approach 5 minutes into the reaction, I draw the reacting solution up into the pipette. It's still reacting in the pipette, so this time is not critical, and I can do this early to allow myself time to use the pipette accurately. Once this is done, the solution is run into the conical flask to stop the reaction and the time noted. Then the solution is titrated with the thiosulfate solution. The thiosulfate reacts with the iodine, which causes the solution to get paler. Once the solution is a pale straw colour, indicating that almost all of the iodine has been removed, starch is added, which gives an intensely coloured complex. The titration now proceeds one drop at a time until the black colour is completely gone. This is repeated every 5 minutes. You can see the reaction proceeding as the solution in the pipette becomes paler as time progresses. Here's the results of the experiment. Each titration needs a calculation to reveal the concentration of iodine in the reacting solution. I'm not going to show those calculations here, but I'll put a link to a video that shows how to do titration calculations in the description below. We can plot the concentration of iodine as a function of time. This shows a straight line graph. In other words, the rate of the reaction, which is the gradient of our graph, doesn't vary. As the reaction proceeds, the concentration of iodine decreases, but the rate of decrease is constant. The rate of the reaction is not affected by the amount of iodine present, despite it being one of the reagents. Initially, this seems strange. Surely the rate of reaction must be a function of the concentration of a reagent. However, this result points to a multi-step reaction in which the slowest step does not involve iodine. Here's one possibility. If the propanone undergoes a rearrangement to form an enol, and then that enol reacts with the iodine, we have a reaction that occurs in 2 steps. If the first step is slower than the second, the overall reaction rate will depend upon the rate of the rearrangement only. The rearrangement is the rate determining step. As soon as any enol is formed, the iodine will react with it. But the reaction cannot proceed any faster than that first step. Hence, we have a reaction rate that doesn't depend upon the concentration of a reagent. A zeroth order reaction.